Hello, everyone. We are Mitsubishi Heavy Industries Thermal Systems, dedicated to the research and development of HVAC systems. Today, we're excited to present our findings and insights under the title Improvement of Cabin Comfort for Battery Electric Vehicles at Low Ambient Temperature by Secondary Loop System Using Conventional Refrigerant. Let's dive into the contents. The presentation is structured into 5 steps, as outlined here. First, let me discuss the motivation behind our study. Lately, both OEMs and suppliers have been adopting heat pump technology, specifically using the conventional refrigerant R1234yf, to enhance the heating efficiency of battery electric vehicles. However, a significant challenge with these conventional heat pump systems is their diminished heating performance in colder ambient temperatures. The primary issue stems from the fact that R1234yf isn't always the best choice for heat pump operations. Consequently, there's ongoing research exploring alternative refrigerants. Another concern with heat pump systems is the potential for the external heat exchanger to frost up in colder conditions. Our research zeroes in on the heating mode by compressor power consumption only within the secondary loop thermal management systems, SLTMS, using the traditional refrigerant for battery electric vehicles. The next slide introduces the concept of SLTMS using R1234yf. Essentially, the SLTMS combines a single refrigerant loop with 2 coolant loops, one for heating and one for cooling. Within the refrigerant loop, there are 2 heat exchangers, one acts as a condenser, and the other as an evaporator. These heat exchangers facilitate the heat transfer between the refrigerant and either the cabin or ambient air, all managed through the coolant. To optimize performance, the SLTMS regulates the flow of coolant to these heat exchangers using flow control valves. This ensures effective heating while preventing frost formation in the outside heat exchanger, OHX. Next, let's delve into the distinctions between SLTMS and conventional heat pump systems. On the left, you'll see the circuit diagram for a typical heat pump system, while the right showcases the SLTMS schematic. The SLTMS excels in delivering effective heating even in colder conditions by controlling the distribution of hot coolant through its evaporator. This control maintains a lower side refrigerant pressure. Contrastingly, conventional heat pump systems face challenges. They require refrigerant, colder than the ambient temperature, to flow to the outside heat exchanger for heat absorption. Given the refrigerant's lower temperature and hence lower density, even with a high-speed compressor, it fails to achieve adequate heating due to reduced refrigerant flow. In the SLTMS approach, the introduction of hot coolant through the evaporator boosts the low-side refrigerant pressure. This results in an enhanced refrigerant flow rate, ensuring consistent heating performance. Additionally, a key advantage of SLTMS is its completely isolated refrigerant circuit from the cabin. This not only facilitates a more compact modular design but also significantly reduces the required refrigerant volume. Let us explain the operations of the SLTMS by focusing on the coolant flow, which can be controlled through valves to facilitate 3 distinct modes. The left diagram shows the cooling mode, the middle one is the heat pump mode, and the right one is the compressor power consumption mode. In all 3 modes, the coolant follows distinct flow circuits, while the refrigerant circuit remains consistent. The refrigerant circuit operates in a cyclical manner, starting with the compression of hot, high-pressure gas in the compressor, followed by condensing in the condenser. This is then expanded in the expansion valve, evaporated in the evaporator, and finally, the cold, low-pressure refrigerant gas returns to the compressor. Let's now delve into the specifics of coolant movement for each mode. In the cooling mode, cold coolant flows through the evaporator, cooling the interior air via the inside heat exchanger. On the other hand, hot coolant moves through the condenser, transferring its heat to the outside air via the outside heat exchanger. In the heat pump mode, hot coolant circulates through the condenser, warming the interior air via the inside heat exchanger. Meanwhile, cold coolant flows through the evaporator, absorbing heat from the outside air through the outside heat exchanger. In the compressor power consumption mode, The process initially resembles the heat pump mode. Hot coolant warms the interior air through the condenser and inside heat exchanger. However, a key difference arises as this hot coolant then passes through the evaporator, elevating the low-side refrigerant pressure. Following this, the cooled coolant bypasses the outside heat exchanger, heading straight back to the condenser. Notably, heating in this mode relies solely on compressor power consumption. A significant advantage is that, since the coolant doesn't flow through the outside heat exchanger, frost formation there is avoided. Moreover, with the conventional refrigerant R1234YF, this heating capability remains consistent irrespective of ambient temperatures. Next, we'll be discussing the heating performance comparison between the compressor power consumption mode and the heat pump mode. On the left graph, the horizontal axis represents the low-side pressure, while the vertical axis indicates the compressor power consumption. Factors influencing compressor power consumption include the refrigerant type, compressor speed, refrigerant suction density, compressor efficiency, displacement amount, and refrigerant enthalpy, as illustrated by the blue line. Once we've determined the target heating performance, we can set both the required compressor power and the necessary low-side pressure. The right figure displays the Morial diagram contrasting the compressor power consumption mode with the heat pump mode. In the diagram, the operating conditions, where the compressor's low pressure is regulated to meet the low-side pressure setting by the SLTMS, are depicted by the dark blue line. Meanwhile, the heat pump mode is represented by the light blue line. It's worth noting that the refrigerant used is R1234YF, and the ambient temperature for this scenario is -20 degrees Celsius. In the heat pump mode, as indicated in the table, the system absorbs heat from the ambient environment. This causes the low-side refrigerant pressure to drop into negative territory, resulting in reduced refrigerant density. Consequently, despite a significant enthalpy difference, the heating performance remains suboptimal. In contrast, the compressor power consumption mode exhibits a smaller enthalpy difference, originating from the difference between the compressor's discharge and suction sides. However, by elevating the low-side pressure to the desired level, we can boost the compressor suction density, increase the refrigerant flow rate, and thereby achieve effective heating performance. In this specific operating condition, the SLTMS exhibits heating performance that is 1.5 times greater than that of the heat pump mode. To reiterate, the SLTMS regulates the suction side refrigerant pressure. By directing hot coolant through the evaporator, it augments the refrigerant flow rate. This enhancement in flow rate, coupled with the increased compressor power consumption within the SLTMS, translates directly to improved heating performance, ensuring efficient and effective heating capabilities. This slide presents the operational modes for SLTMS and conventional heat pump systems across varying ambient temperatures. On the graph, the horizontal axis represents the ambient temperature, while the vertical axis indicates performance. The light blue region denotes the performance level required for a comfortable cabin. The dark blue region signifies the maximum achievable performance by each system. The left graph illustrates a conventional heat pump system equipped with an electric heater, which necessitates auxiliary heating at colder ambient temperatures. Conversely, the right graph depicts SLTMS. Remarkably, SLTMS can consistently maintain optimal heating performance irrespective of the ambient temperature, achieved by regulating the suction side pressure in the refrigerant loop during colder conditions. This slide highlights the 5 key features and benefits of SLTMS. Sufficient heating performance without electric heater. Through precise control of coolant flow to heat exchangers via valves, SLTMS achieves robust heating using only compressor power consumption, eliminating the need for an electric heater. Continuous heating operation without frosting. By relying solely on compressor power at colder ambient temperatures, SLTMS prevents frosting of the outside heat exchanger, ensuring uninterrupted heating. Compact refrigerant loop. SLTMS's refrigerant loop is entirely isolated from the cabin. This design facilitates a streamlined modular approach and significantly reduces refrigerant volume. Additionally, there's no risk of refrigerant migration within the heat exchanger or plumbing. Versatile heating and cooling operations through coolant. Beyond heating, SLTMS offers cooling capabilities during fast battery charging and can recover waste heat from in-vehicle components like the motor and inverter. Future-proof for alternative refrigerants, SLTMS is primed to accommodate upcoming refrigerants like R290 and HFO mixtures. By keeping these potentially flammable refrigerants outside the cabin, SLTMS enhances safety while optimizing heating efficiency and performance. Moving forward, let's delve into the results derived from the 1D model simulation. Here are the simulation parameters and conditions using the GT Suite tool. Compressor power consumption heating mode. Ambient temperature is -20 degrees Celsius. Compressor speed is 9000 RPM. Coolant flow rate is 15 liters/min. Outside heat exchanger air flow rate is 2500 m superscript 3/h. Inside heat exchanger air flow rate, heating mode, is 250 m superscript 3/h. Inside heat exchanger air flow rate, cooling mode, is 500 m superscript 3/h. In heat pump mode, ambient temperature is -5 degrees Celsius. Note, other parameters remain the same as mentioned above. Cooling mode. Ambient temperature is 35 degrees Celsius. Note, other parameters remain consistent with the previous modes. Let's now examine the simulation outcomes specifically for the compressor power consumption heating mode at an ambient temperature of -20 degrees Celsius. The left two graphs depict the refrigerant pressure and coolant flow rate within the evaporator and condenser. The horizontal axis represents time. From the upper left graph, if the evaporator's low-side refrigerant pressure is insufficient, introducing hot coolant can elevate this pressure. By adjusting the coolant flow rate, the desired pressure level can be attained. From the lower left graph, if the condenser's high-side refrigerant pressure falls below the desired level, reducing the flow rate of cold coolant within the condenser can elevate this pressure. By further adjusting the coolant flow rate, the target pressure is achieved. Additionally, the right graph displays both the heating performance and compressor power consumption. As evident from the graph, the heating performance is consistently achieved through compressor power consumption, irrespective of the ambient temperature. This page presents the results from our bench test, where we assessed the heating performance of the SLTMS using compressor power consumption at a chilly ambient temperature of -20 degrees Celsius with R1234YF refrigerant. From the feasibility test, we observed that the inside heat exchanger delivered a performance of 8.6 kilowatts at -20 degrees Celsius ambient temperature, while the compressor power consumption stood at 9.5 kilowatts. This yields a coefficient of performance, COP, of 0.9. Notably, there was a heat loss of 0.9 kilowatts. This elevated heat loss can be attributed to the extended plumbing setup utilized in the bench test. This slide illustrates the bench test layout. It features a refrigerant circuit comprised of a compressor, a coolant circuit equipped with a pump, and both inside and outside heat exchangers. This slide presents the bench test results across the three operating modes. In the cooling mode, we achieved a cooling performance of 5.6 kilowatts at an ambient temperature of 35 degrees Celsius. In the heat pump mode, we delivered a heating performance of 5.4 kilowatts with an ambient temperature of -5 degrees Celsius. In the compressor power consumption mode, we demonstrated the highest heating performance of 8.6 kilowatts at an ambient temperature of -20 degrees Celsius. The results underscore SLTMS's capability to deliver satisfactory performance across all operational modes. This slide presents the bench test results plotted on a memorial diagram, focusing on the compressor power consumption heating mode. The specific test conditions are: ambient temperature is -20 degrees Celsius. Refrigerant is R1234YF. Compressor speed is 9000 revolutions per minute. Inside heat exchanger air flow rate is 300 cubic meters per hour. From the data showcased in this slide, it's evident that the low-side refrigerant pressure stands at 0.5 MPa. This results in SLTMS experiencing a heightened refrigerant density and an increased refrigerant flow rate. Consequently, with the use of R1234YF refrigerant, SLTMS efficiently achieves commendable heating performance even at such low ambient temperatures. This slide offers a concise summary of SLTMS's capabilities. Efficient heating performance. SLTMS achieves notable heating results at low ambient temperatures using the R1234YF refrigerant, eliminating the need for an electric heater. Additionally, it ensures uninterrupted heating without any frost on the outside heat exchanger. Performance metrics. At -5 degrees Celsius ambient temperature, SLTMS delivers a heating performance of 5.4 kilowatts. Conversely, in warmer conditions at 35 degrees Celsius ambient temperature, it provides a cooling performance of 5.6 kilowatts. Refrigerant loop design. The refrigerant loop boasts a compact modular design, enabling a significant reduction in refrigerant volume. Importantly, this design prevents any refrigerant migration within the heat exchanger or plumbing. Temperature control flexibility. SLTMS offers versatile temperature control capabilities. It can regulate the coolant temperature regardless of the ambient conditions. This ensures adaptable temperature supply to various components such as batteries, e-motors, inverters, and more. In conclusion, while our current system demonstrates promising results, there are areas that warrant further enhancement. Cool-down and warm-up performance. The current cool-down and warm-up rates are less efficient compared to conventional cycles. This aspect requires optimization. Cooling configuration. During rapid battery charging, there's a need to devise a specialized cooling setup to ensure the battery remains at an optimal temperature during fast charging processes. Heat recovery potential. Leveraging waste heat from components like the e-motor and inverter presents an opportunity. By channeling this waste heat to the suction side refrigerant pressure, we can enhance heating performance while concurrently reducing compressor power consumption. Potential for flammable refrigerants. If we transition to flammable refrigerants like R290 in the future, it's imperative to emphasize safety. By ensuring the refrigerant remains outside the cabin, we can bolster safety measures. Moreover, such a transition could further enhance both heating efficiency and performance. Thank you for watching. That concludes our presentation. If anyone has any questions or would like further clarification, please don't hesitate to make comments or send messages to this account. Thank you once again for your time.